So the objective of today's session is I want to give some results, nothing but the theorem statements. Then based on previous class results, I want to take some problems on it. Then I will take the other problems. So this is the ideology for today's session. Okay? Is that fine? Right. So let us take some results that suppose I have a sequence Sn and I know that it is convergent to S. Now what happens if you consider the average sequence, that is S1 plus S2 plus so on plus Sn by n, then it is also converges to S. So what is the first statement? I have a sequence which is converging to S. Then if you consider the average, then the average is also converging to S. That is one result. So this result is called Cauchy's first theorem on limits. That was Cauchy's first theorem on limits. So take a note of that. Then followed by this result, we can say the other one, that if you consider a sequence which contains all positive values, the sequence contains all positive values, and you know that the sequence has a limit L, then if you consider the geometric mean, then it also converges to the L. Yes? These are the results, nothing but Cauchy's theorems on limits. Since the proof of the theorem is not important, only problem solving is our concern, so I am giving the results. Right. So this is the first one. Any queries with regard to this? Yes or no? No. Right. Now, this is the other one. This one gives about the average, in other words, the arithmetic mean. This one talks about the geometric mean. The other result is that if you have a sequence Sn and each term in the sequence is positive, and if you calculate the ratio, if you calculate the terms ratio in the sequence, if they converge to L, Sn plus 1 by Sn, limit n tends to infinity, Sn plus 1 by Sn equals to L, then the nth root limit is also L. Limit n tends to infinity, Sn whole power 1 by n equals to L. This is another result. So take a note of that. So can I take the other one? Right. The other one is called ratio test. So you take a sequence of positive values and you take the ratio. The ratio tends to L. So what ratio test says? Sn is positive for all terms and the ratio tends to L. Then what happens? Observing the limit, we say that if its limit value is less than 1, then the sequence is converging to 0. And if the ratio value is greater than 1, we say that the sequence is divergent, it tends to infinity. So you please take a note of this result, ratio test. Right. So these are the results I want to wish to give for you. And then one result is, if you have a sequence which is convergent, then you can say that you will get a subsequence of it converging to same limit. In other words, if you want to prove that the sequence is convergent, whatever the subsequence you consider for it, it tends to the same limit. That is one result. So I think at present these results are sufficient for you. Then let us go for some problems, right? So have you taken a note of it? Yeah. Since yesterday we have done some problems with respect to, monotone convergence theorem, and I have given the concept of sandwich theorem. So let us take some problems on sandwich theorem. And it is clear that the concept of sandwich theorem is, whenever you have three sequences having an hierarchy, Sn less than or equal to Un less than or equal to Tn, if the lower and upper sequences are tending to one limit, the same limit, the middle one also tends to the same limit. That is the concept of sandwich theorem. Am I correct? Yeah. So this is my problem. Limit n tends to infinity, square root of n square plus n minus n equal to 1 by 2. Please understand that in examination point of view, he didn't mention using sandwich theorem solve the problem. He never give like that. He will simply mention whether to verify, or he will mention like this. The technique is user defined. You can apply any kind of technique, right? Okay. Now, since this is our nth term in the sequence, so let us take that Sn is equal to root of n square plus n minus n. Now usually for this kind of problems, we go for the rationalization. So let us rationalize this. So if you rationalize this, it is equals to so simplifying the numerator, you say that the result is am I correct? Yeah. Now what happens? You can further simplify by cancelling n there. So this is equals to 1 by root of 2 comma n square there, 1 plus 1 by n plus 1. I have cancelled n in the numerator as well as in the denominator. So this is my term Sn. Now what happens for this Sn? It is my responsibility to show that Sn has an upper bound as well as a lower bound. Nothing but upper bound is a sequence and lower bound is sequence. And if I am able to prove that these two values tend to the same number 1 by 2, then I am done. As per Sandwich theorem, this also tends to 1 by 2. That is the objective of the problem. Fine. Any queries? Yeah. So here we goes with a construction. Construction is just like observing the terms here, the part of Sn. We go with our own kind of construction. Generally, we cannot define a specific procedure for it. It is just like getting an upper bound and lower bound for the term Sn. So I will go like this. I think it is understandable, the construction part. I can say that 1 is less than root of 1 plus 1 by n. Yes? Because I have taken the term here, observing this term in the denominator. Yeah. Since always root x is less than x, I can say that this is less than 1 plus 1 by n. So what happens? Since 1 is there in denominator, you add 1 here. So 2 is less than root of 1 plus 1 by n plus 1, which is less than 2 plus 1 by n. Since it is reciprocal, you take the reciprocal. So if you consider LCM, this is 2n plus 1 by n, so n by 2n plus 1. Accepted? Any queries? Yeah. So from this you can say that you can cancel n here. 1 by 2 plus 1 by n is less than, this is nothing but Sn is less than, this is 1 by 2. Right. So you have observed two sequences here. One is the constant sequence 1 by 2. Another one is the sequence 1 by 2 plus 1 by n. And our sequence is bounded here. So if you apply the limit for the lower and upper ones, so lower one converges to 1 by 2 and upper one converges to 1 by 2. Accepted? Yes or no? So by Sandwich theorem, Sn also converges to 1 by 2. So we say that limit n tends to infinity, root of n square plus n minus n equals to 1 by 2. That was the conclusion. Okay? Right. So can I take the other problem? So please take a note of it. Then the other one is this is my next problem. So please take a note of it. So we have to prove that the limit of this sequence equal to 0. The bracketed expression is nothing but the nth term of the sequence. We should take like that. So the nth term Sn of the sequence is taken as It is 1 by n plus n whole square, nothing but 2n whole square you can take. I just have written the form as it is. So we need to go for a construction such that Sn has a lower bound as well as upper bound. How I am going to do? If you observe the denominator, Sn is nothing but sum of the terms, where if you observe 1, 2, 3 up to n values are taken here. So I will take that for 1 less than or equal to m less than or equal to n. Since denominator contains n plus 1, so you add n for this thing. So n plus 1 is less than or equal to n plus m less than or equal to n plus n. Since the square is there, you go for squaring. Since reciprocal is there, you go for the reciprocal. Is this fine? In other words, if you write from this place onwards, it is 2n. So you can have so here you have, if you substitute m is equal to, it is only based on observing the terms pattern. That's it. There is no special ideology is there. So let us say one thing. Suppose Sn is just mentioned like a single term. In the previous example, the problem what I have taken, it is given that n square plus n minus n, it is just like a single term. So what happened here? I have rationalized this because to avoid the square root. Then observing the term pattern, I build two terms. One is bigger than this and one is smaller than this. Isn't it? So here if you observe, Sn is not a single term. It is having sum of the terms. So if you want to build an upper bound as well as a lower bound, the technique is nothing but, for each term for Sn, can I have to specify a lower bound or upper bound? For the first term, 1 by n plus 1 whole square, second term, 1 by n plus 2 whole square, and so on, last term. So it is just like I can say that, say if for the value A, I have specified the lower and upper bounds. For B also I have specified. For C also I have specified. So what happens? Sum of the lower bounds, sum of the upper bounds is nothing but lower upper bound of, accepted? The logic. If we have a set of inequalities, if we have summed them, the same technique we are following here. So that all I want to show here. Is this concept clear for everyone? 1 less than or equal to 1 m less than or equal to n is taken from the Sn part, because in the denominator 1, 2, 3 up to n values are added, isn't it? So if you take an arbitrary term, it will be 1 by m plus m whole square. You can take any index 1 by n plus k whole square. So for each n plus k, you need to specify a lower and upper value. Accepted? Right. So let us write this elaborately for your understanding. So if you take m is equal to 1 here, you can say that so in this expression, if you take m is equal to 2, it will come as Accepted? So what I am showing, for each term in this sum, I am specifying the lower and upper bounds. So on, if you go for the last one, this is the thing. For the first term, I have specified upper bounds. Second term, upper bound, lower bound, third bound, and so on. For the last term, this is the lower one, this is the upper one. Accepted? So, if I sum up all these inequalities, the sum of the middle ones is nothing but Sn. Do you agree? Now, how many inequalities there are there here? N inequalities, isn't it? Because I have taken the index from 1 to n, 1 less than or equal to m less than or equal to n. So, after framing this relation, I got n inequalities. I am adding the n inequalities. So, what is my result here? On the left hand side, the value is same. I am adding it for n times. It is nothing but n by 4n square. It is less than or equal to, if you sum up all the middle ones, it is nothing but our Sn. It is less than or equal to, if you sum up all these things, you are adding n times the value n by n plus 1 whole square. Accepted? Any questions? Yeah. So you please take a note of that. Then I will write one final step. Then we can conclude the problem. Yeah. So this is my first part, this is my second part, and this is my third part. Yeah. Now, if you observe this here, you can cancel 1 n here. So 1 by 4n remains. So I want to modify this relation a little. So you can write it as, because we can say that this value is less than this thing, because n plus 1 whole square is less than n square. So, sorry, 1 by n plus 1 whole square is less than 1 by n square. So this will be modified like this. So you can cancel one thing here. So 1 by 4n is less than or equal to Sn is less than or equal to 1 by n. So by applying limit for the lower and upper sequences, it converges to 0. It tends to 0. By sandwich theorem, Sn also tends to 0. In exam also, we put the same symbols. After framing the sequence pattern like this, we indicate a mark with an arrow that this is tending to this number, this is tending to this number. Therefore, by sandwich theorem, Sn tends to the same number. That we write in exam. Fine. I think everyone is clear with this thing. So please take a note of it. Then I want to go a little interesting problem. Yes, we can apply that thing also. So straight away you can apply limit here. You will get 0. That is also accepted. But I am giving a little modification. That's the case. Sometimes if you get a number which is not tending to the required limit, then what happens? I am saying that you can modify the bounds furthermore. You cannot restrict yourself to the bound which is obtained there only. You can find a better bound than that. Yes, we follow the same procedure. whatever I have written on the board, you exactly write the same thing on paper. You will be given marks. Step 1, step 2, step 3, and that is step 4. First is building a relation. Second, summing up the inequalities. Third, getting a sequence pattern. And fourth, applying sandwich theorem. Please understand one thing, that for this problem, this is the procedure. For the other problem, the procedure is different. So we should remember one thing, that as and when a particular problem is given to you, what kind of procedure is more appropriate for this? That is the issue. So how can we say that the answer is available in the second step? So from this straight away you can say that after framing the inequalities without summing them, how can you get Sn is this? This relation states that for each term in Sn, I have a lower bound and upper bound. Yes, 1 by n plus 1 is tending to 0. Yes. So if let us take, if you have taken only this inequality, is this Sn? So Sn means what? Sum of the n terms, the terms which are given there in the procedure. So you should prove that for each term you have calculated a bound. So if you sum up the terms, then only you will get for the whole Sn the smallest and the highest bounds. That's the issue. If you apply limit for one term in Sn only, you have calculated that. I think you got the point. Right. So can I take the other one? Fine. The question is, discuss the nature of the sequence r power n where -1 less than r less than or equal to 1. I think this problem is given in one of the previous years. I hope so. Discuss the nature of the sequence r power n where -1 less than r less than or equal to 1. So what is the question concept here? I am going to take any number from -1 to 1. Let me say I have taken 0.2. So the sequence r power n is nothing but 0.2, 0.2 square, 0.2 cube, so on. This is my sequence r power n. If I take r is equal to 1, what is my sequence? 1 power 1, 1 square, 1 cube, and so on. In other words, I am discussing the nature of the sequences which are given by this pattern, okay, where r has a limit, the boundary, -1 to 1. Accepted all? The question objective. So if you observe the choice of r is bigger than -1 and equivalent to 1. Up to that you can take any real number. So I am going to consider this as, if you take -1 up to 1 I can take. So I am bifurcating the discussion of the nature as, if I take r between these two, what happens? Up to this portion to this portion. And if I take r in this part, what happens? And the other numbers left are nothing but r equal to 0 and r equal to 1. So that I have covered each and every real number which is specified in this given range. Accepted? Yes. So I am discussing the nature by taking R which is bigger than 0, smaller than 1. I am discussing the nature if I take R which is bigger than -1, smaller than 0. And what happens if R equal to 0 and if R equal to 1? So total 4 things I am discussing here, so that it covers each and every real number within the range specified there. Accepted? Yeah. Now, if R equal to 0, R power n is nothing but a constant sequence 0. Accepted? If you take R equal to 0, R power n is nothing but 0, 0, 0, so on, which is a constant sequence which tends to 0. Yes or no? So if you take R equal to 1, then R power n is nothing but another constant sequence. R power n, the terms in the sequence are nothing but 1, 1, 1, 1, 1, so on. So these two are nothing but the constant sequences. So limit of the sequence is 0, limit of the sequence is 1. So both are convergent sequences. Accepted? Right. Now I am taking the case if R lies between 0 and 1, bigger than 0, smaller than 1. That case I am taking. So the two cases there I have shown are nothing but the trivial cases. Obviously they are convergent because it is a constant sequence, always tending to the unique limit, the number itself. Right. So take the case that 0 is less than or less than 1. So I can say that if we have taken a number, say R is equal to 0.5, can you write that this is nothing but 1 by 2? Yes. Again you can write that the same 0.5 can be written as 1 by 1 plus 1. So whatever the number you take, usually you can write it as R as 1 by 1 plus something. You can take 0.1, 0.2, 0.3, 0.4, 0.5, whatever it is. Whatever the R you take, it is possible to write that R is equal to 1 by 1 plus something. Accepted? Everyone? Any questions, please? Right. So this something I am taking it as H. So whatever the R value you choose from between 0 to 1, you can mention R as 1 by 1 plus H. So what happens if you consider the sequence R power n? It is nothing but 1 by 1 plus H whole power n. Now for the denominator part, you apply the binomial expansion. Accepted? The expansion form? I have applied the denominator, expanded it using the binomial form, the binomial theorem. 1 plus H whole power n. So nc naught x power n, nc1 x power n into y power n, like that. Please understand, our objective is not to simplify this expression. Our objective is, I have a sequence, I want to apply sandwich theorem here so that I am able to find or decide its convergence nature. So I can say that the value whatever here it is written, it is less than 1 by 1 plus nh. Yes, because the denominator is bigger than this. Again, you can say that this is less than 1 by nh. Yes or no? Because I am applying only sandwich theorem here. I just want a construction here. That's it. So what happens? I can mention that 0 is less than r power n is less than 1 by nh, whatever the r value you take from 0 to 1. That is the ideology. So you can treat that 0 as a constant sequence. It tends to 0. If you apply limit here, it tends to 0. By sandwich theorem, the middle one also tends to 0. Therefore, the technique of sandwich theorem states that whenever you take a value r between 0 and 1, the sequence always converges to 0. Is that clear? So I have proved the three cases: r equal to 0, r equal to 1, and r is lying between 0 and 1. I am left with one more case, that I have to verify the convergence when r is greater than -1 and less than 0. This part you are asking? Yeah. So you want to decide the nature of the sequence r power n. I have chosen this case. If I want to apply sandwich theorem for r power n, I need to specify two bounds: the sequence which is bigger than this, the sequence which is smaller than this. Since r is between these two, if you calculate r power n, always it is positive, isn't it? So I can write trivially that 0 is less than r power n is less than 1 by nh. This is my result after simplifying this term. So if you apply sandwich theorem, I got the bounds here. This is one bound and this is another bound. So 0, you treat it as a sequence, not a number. It is the 0 sequence. So it is tending to 0. The constant sequence 0 it is. 1 by nh, it is a sequence. If you apply the limit is 0. So for the lower sequence, the limit is 0. For the upper sequence, the limit is 0. So by sandwich theorem, for r power n, the limit is 0. So it is true for every r between 0 and 1. Because we have chosen r between 0 and 1. It will be any number between them. That's it. Okay? So don't feel that it is 0. It is the 0 sequence. 0, 0, 0, 0. The constant sequence. It is not a number. Right. So let us take the other part. So you take that -1 less than or less than 0. In this case, I am going to verify the convergence. Since r is a negative number, you can write it as r as -s, nothing but -1 into s. Say yes or no. Now r power n, if you consider, you are taking whole power n of this. Now what you proved earlier, whenever you have a number between 0 and 1, it tends to 0. This result you have obtained in the previous case. Now what happens? From this statement, we can say that say yes or no. If you multiply both sides with minus 0, can we say like that? I can say, yeah. For this, if you multiply with minus 1, then what happens? It is nothing but 0 is less than s is less than 1. This I have considered. For r, you can write like this. From this, you can say by multiplying with minus, you can write like this. This is my output. Accepted. Are you getting my concept? Yeah. So, using the previous case study, observing that S is lying between 0 and 1, immediately I can say that S power n tends to 0 as per the previous case. Therefore, if you consider r power n, it is nothing but minus 1 whole power n into s power n. So, it tends to 0. How I am saying that it tends to 0? Because in the previous class, I have given some results that S power n is tending to 0. Is that part clear? You have a doubt? This thing we have proved earlier. Yes, in the third case we have proved that by taking the binomial expression. Accepted? Yeah. So what does it mean? Whatever the number you take from 0 to 1, if you consider the sequence r power n, it is tending to 0. Let me say I have taken L between 0 to 1. So 0 is less than, L is less than 1. So from that statement I can say that L power n converges to 0. If I have taken 0 is less than, P is less than 1. So from this discussion I can say that P power n converges to 0. Like that, I got 0 is less than, S is less than 1. So I can say that S power n converges to 0, the sequence. Accepted. Are you getting the ideology? So the third case gives the result that you take any number which is bigger than 0 and smaller than 1. The corresponding sequence r power n always tending to 0. That is the overall result you obtained in the previous case. So here I have the number S which is lying between 0 and 1. From that strategy, I say that S power n tends to 0, the sequence. Accepted. Fine. Now I want to discuss the nature of r power n. So you consider r power n there. So r power n is nothing but, so here you have r is equal to minus 1 into s. So if you consider r power n, it is minus 1 whole power n into s power n. Right. So in the previous results what I have given in the last session, if you have a sequence and another sequence is a bounded one, then the product sequence is convergent. You have a result. I have given that one sequence is convergent, another sequence is bounded. If you consider the product, the result is tending to the same limit. So here minus 1 whole power n is a bounded sequence. S power n is a convergent sequence tending to 0. So the product sequence will tend to 0. That was the result. Clear? So the task of the problem is completed. So as and when you take R from this to this, always the sequence is convergent. That was the conclusion of the problem. By taking the 4 cases, 2 cases are trivial. They are nothing but the constant sequence. 1 case we applied the binomial expansion. For the last case, by writing like this, you proved the result by taking a small result that if one is converging to 0, another one is bounded, the product is convergent. That's it. So can I take the other problem then? Yes, that is also accepted. Why not? You can apply any strategy. You can apply any strategy. The thing is, which is more appropriate there? That's it. That's why in the first session of my class, I mentioned that for solving a problem, there are many strategies. You can apply anything. The conclusion is you should be able to get the answer. That's it. That is the only difficulty in analysis. That's why for majority of the problems or questions posed on analysis, so if you want to say that R power n, you need to get the sequence values first. See, the concept why I have applied sandwich theorem is, let me say, this is R power n. So this is Sn you want to take, right? Sn plus 1 is nothing but R power n plus 1. You have to verify whether it is convergent or divergent. So you need to mention it is either increasing or decreasing. So you can consider the difference between them. Now what you can say about the difference? Is it positive or negative? If you have taken the case that 0 is less than or less than, what about this thing? Is it positive or negative? Positive, right? So you can say that Sn is greater than Sn plus 1. So it is a decreasing sequence. Yeah. So now you need to specify the lower bound. Now here the task comes. How to get that this is the lower bound of it? So you have to verify that every term R power n has a lower bound. How to get the value here? I think you caught my question. Because R is the variable here. So you can take R is equal to 0.2, 0.3, 0.4, 0.5, anything. If you take R is equal to 0.5, what will be the lower bound of it? For R power n, you should be able to say that every value is bigger than this. So trivial, you are going to mention that it is 0. The lower bound is 0, trivially. But you need to prove it logically, right? You can apply induction or anything, but you have to say that always R power n is bigger than this. That's why I have applied the technique of sandwich theorem. Because not only for one single R, you are proving for every R there. Right. So since it is a lengthy discussion over the problem, I just want to take some small problems over the results which are given today, right? I think though they will be somewhat interesting. Because once you start thinking about one single problem, it takes much time. So this is my problem, that you take Sn is equal to n by n plus 1. Or say like this, n plus 1 by n you take, right? Now start writing the sequence values. What will be S1? Two by 1, isn't it? The first term of the sequence. So what is S2? 3 by 2. Are you getting or not? Right. So on. This is the nth term, Sn. Right. So if you calculate limit Sn, what is the value for this one? It is nothing but limit n tends to infinity 1 plus 1 by n, the value equals to 1. Accepted all. Right. So why I have chosen this? Because there is a small result that limit nth root n is equal to 1. Have you known this? Yes or no? So if you consider the product, I have given this type of result earlier, right? So if you substitute all the values there and if you simplify, what will be the value? So if you simplify all the values, what you are going to get? Is that n? Because the terms gets cancelled. So on. Will you get 1 there or not? The value n. So let us do a modification here. So if you have taken the sequence like this, say n by n minus 1, say just have a modification there. I want to define in a different way. No. Just I am taking for a different notion. Apart from defining like this, can I define in a better way? Just hold for a second. I want to take the application of the theorems what I have taken. Yeah. So let us apply a different limit here. Yeah. I want to apply a different thing here. So you fix the same question, right? Sn is equal to n plus 1 by n. S1 is equal to 2 by 1. S2 is equal to 3 by 2, so on. I have calculated limit Sn. That is also 1. Apart from this, if you go for limit n tends to infinity Sn plus 1 by Sn, what will be the value? Can you say? Just want to, yeah. Let us define sorry, I just want to change this pattern. Sorry, I define like this. So this I want to prove like this. You can have a pattern like so my concept is nothing but just proving limit nth root n equal to 1. So for this we have two strategies that we can prove like this using the geometric mean technique, one type. Another one is the ratio test technique. Both you have. I have given the Cauchy's theorem limits, Cauchy's theorem results, right? One is for average, another one is nth root Sn is equal to L. I have given a result like this. So using this technique, I have proved that limit nth root n is equal to 1. This is one kind of strategy. Okay. So another one is you can apply the geometry mean technique also. So by taking that 1 into 2 by 1 into 3 by 2 into so on Sn, S1 into S2 into so on Sn, whole power 1 by n is also equals to 1, where limit Sn is equal to 1. That also you can prove. I hope so. You can do like that. So majority of the cases we prefer this technique. The result is, this is the result, you take a note of this. Proof is not required. If you are interested, this is the proof you can follow. This is the other strategy. So this thing we make use while proving some of the results. Limit nth root n equal to 1. Okay. Is this acceptable? Right? Now just hold for some problems that the concept of giving that result is, this is my problem. Can I make space here? So if I have given that, prove that limit n tends to infinity this is my problem I have given there. So limit n tends to infinity 1 by n into 1 plus 2 power 1 by 2 plus 3 power 1 by 3 plus so on plus n power 1 by n equal to 1. If this is my problem, right? So how I am going to prove? So here I prove that if I have taken Sn is equal to n power 1 by n, since I know that limit nth root n is 1, that is limit n power 1 by n is 1, limit n tends to infinity Sn is equal to 1. As I know the results of the Cauchy's theorem, whenever the sequence has limit existed, you can take the geometric mean as well as the arithmetic mean. So this is nothing but arithmetic mean of the sequence. So limit n tends to infinity S1 plus S2 plus so on plus Sn by n is equal to 1. So it is nothing but limit n tends to infinity 1 by n into the given sequence. That's it. So to prove this problem, I have taken that concept earlier. So initially, if you have seen that, what about this sequence? What is the strategy here? The outline idea is we are going to make use of the results which you have learned earlier. That's it. Okay. So whenever you have a sequence limit 1, if we calculate the average, the arithmetic mean, say the value is also 1. It is tending to the same limit. So if you consider S1, it is nothing but 1. S2, 2 power 1 by 2. How it is taken? Because of the form. S2 is 2 power 1 by 2. S3 is 3 power 1 by 3, so on. Sn is n power 1 by n. So average is whole by n. The value is also equal to 1. Okay. Is this clear? Any queries to anyone? That's why it is required to prove. That's why I have taken that earlier. You have to show that limit n through 10 is equal to 1. Otherwise, straight away I have proved this. But you have observed the length of the problem is nothing but just 3 steps. 1, 2, 3. So if the same problem is given for 10 marks, it will not be awarded for you if you have written only 3 lines, right? You have to prove this part also. How you have shown that limit n through 10 is equal to 1? How do you know? That's it. So can I take the other part? Right? So prove that limit n tends to infinity x power n by n factorial equal to 0 where x is greater than 0. This is the other problem. Right. So usually as and when a problem consists of the terms power n, we always use the technique of ratio test. The concept of limit Sn plus 1 by Sn. For majority of the problems, we use this technique. So let us also apply the same technique here. So you have taken that Sn is equal to x power n by n factorial and Sn plus 1 is equal to x power n plus 1 by n plus 1 factorial. So if you calculate the ratio, Sn plus 1 by Sn is equal to x power n plus 1 by n plus 1 factorial into you can write it as n factorial by x power n. So on simplifying will be x by n plus 1. The terms gets cancelled. So if you apply limit, since x is not getting under the limit, so it will be x into limit 1 by n plus 1. So this is equal to x into 0, 0. Accepted? Yes or no? So what is the concept of ratio test? As and when you consider the ratio Sn plus 1 by Sn, you calculate the limit. If the limit is existed and the value is less than 1, then we say that the sequence will converge to 0. That is the concept of ratio test. Could you recollect? Which is given earlier. Therefore, I have evaluated the limit of the ratio. The limit is nothing but 0. Since 0 is less than 1, from ratio test, I can say that the sequence is converging to 0. Therefore, limit n tends to infinity x power n by n factorial tends to 0. That is the conclusion. Okay? Right. So let us take something interesting. So we have a sequence Sn is equal to 1 plus 1 by n whole power n. You take the sequence Sn is equal to 1 plus 1 by n whole power n. So this sequence is convergent. We apply the technique of monotone convergence theorem. I simply give the posters in Telegram. You go through it. It is very easy. So what happens there? The limit of the sequence is lying between 2 and 3. So in sequences, it converges to 0 in the ratio test. That is the object of ratio test, isn't it? And one thing is, the sequence which you have considered is always positive. You have to take the sequence. The statement is like this. I have sequence Sn which is greater than 0. And consider limit Sn plus 1 by Sn. It must be equal to L. Then I am defining the two things. If the limit value is less than 1, the sequence tends to 0. If the limit value is greater than 1, the sequence diverges. This is the statement of ratio test. So please check on that. Now you accept with that ideology what I have mentioned? Yeah. So coming to this, the sequence 1 plus 1 by n whole power n, what you take, by applying monotone convergence theorem, it will become convergent. I give the posters to you later. The limit of the sequence is lying between the numbers 2 and 3. Say you know the symbol E. The value is 2.718 something, right? The value of E. So E is nothing but the limit of the sequence 1 plus 1 by n whole power n. In other words, n plus 1 by n whole power n, the limit of the sequence. So what happens? This is a useful result. 1 plus 1 by n whole power n tends to the limit E, right? So as and when a problem consists of this kind of numbers, we make use of the limit condition, right? So you take a note of that. Limit n tends to infinity 1 plus 1 by n whole power n is equal to E. You take a note of this condition. It is most important. For many problems, we use this criteria. So based on this, we talk of a small problem here. The limit value is approximately 2.718 and we are indicating with the symbol E. Proof I will give you. That's what I have mentioned. It is just like monotone convergence theorem. I give the postage. Because you know how to prove, so there is no need to explain that separately. That's my intention. If you want a explanation class, tomorrow I will take on that. Okay? I will give the proof, you can check in Telegram. Right. So the problem is prove that limit n tends to infinity n factorial by n power n equal to 0. This is the problem. Limit n tends to infinity n factorial by n power n equals to 0. So if you define the terms there, Sn is equal to n factorial by n power n. Yes, n plus 1 is equal to n plus 1 factorial by n plus 1 whole power n plus 1. So if we calculate the ratio, Sn plus 1 by Sn equals to so simplifying the terms, you can write it as now what happens? I can cancel n factorial there. I can cancel n plus 1 here. So if you common n inside, Sn plus 1 by Sn is equal to again n power n gets cancelled. This will remain. Accepted? Please check. Yeah. So if you apply limit to the ratio, so for limit, as you know, the result which I have given earlier, it is nothing but 1 by E. In exam, there is no need to write that limit of 1 plus 1 by n whole power n is equal to E, the proof is not required. We just mentioned that we know that limit 1 plus 1 by n whole power n is equal to e. That we mentioned. That's it. Proof not required unless it is asked in the question. So since e is nothing but 2.7 or something, so 1 by this is always the value less than 1. Accepted? So I have applied the ratio test. I calculated the limit. The limit existed here and the value is less than 1. Therefore, by ratio test, it converges to 0. That was the solution. Okay? Is this part clear? So let us wind up our session here. So tomorrow I want to take one interesting problem on monotone convergence theorem concept. Later I will take some set of problems based on this test, ratio test and other Cauchy's theorem test. And we discuss the concept of Cauchy's sequence today. Tomorrow, Cauchy's sequence tomorrow. So later we conclude the whole sequences chapter. That is the summary of the sequences chapter we have discussed. So in the upcoming sessions, we will discuss about the other chapter, infinite series. So that is my schedule, the upcoming schedule. Right? So let us wind up our session here. If you have any other queries, you can ask. I hope that that explanation is enough for you. Do you need any elaboration? So we need to understand one thing, that straight away, the question is given straight away, you can apply the limit, you can calculate it. But usually questions of that type will never be given in the exam. So did you solve this question using the calculus what you have mentioned earlier? Did you solve this type of question earlier, say? I mean, in differential calculus, the +2 calculus. That's why it is obviously a different question, right? So definitely we apply this ideology. Such type questions you can expect in the paper 1 calculus part, not in paper 2. It is based on real analysis. Okay. So any other questions for anybody? So thanks to very much, and thanks for your good listening. So let us meet tomorrow. If you are getting a little boredom, you please mention. Because initially analysis looks like somewhat dry subject. Later you will get interested over this. Because this type of strategy you didn't come across earlier in your study. Accepted? It is totally different thing. Fine. That's all.